Welcome you all again. We'll be discussing the next important question, application of Gauss's law, that is the electric field due to thin infinite plane charged sheet. Like electric field, this is a surface charge density. This is related to surface charge density. Surface charge density. And we have to find out the electric field using Gauss's law for a thin infinite charged sheet, and it has been asked so many times so far in the previous examinations, and we are expecting it again. So let us discuss now. Let's consider a thin sheet like this. It's a thin charged sheet. First we'll draw. We'll draw the dotted line is representing that it's infinite long. The positively charges are uniformly distributed in this thin charged sheet. The positive charges. And now the electric field is calculated due to this infinite charged sheet. And electric field is calculated at a point. Say suppose this is a point which at a distance, suppose r or something, you can write r from the thin sheet. At this point we are supposed to find, that's this point be P, where the electric field due to this sheet is to be calculated. But we are using Gauss's law, and for Gauss's law we need a Gaussian surface, closed surface. So what we will draw? We will draw a Gaussian surface, a cylindrical Gaussian surface on this very point. That's like this. Let this be a cylindrical Gaussian surface. This is the cylindrical Gaussian surface. यहाँ से मैं डॉट डालता हूँ ताकि ये दूसरी साइड से जा रहा है. This cylinder will go inside the other side of this sheet. This is the Gaussian cylindrical surface, Gaussian surface enclosing this charge, and we have to find out the electric field at any point that we consider this point. So I again repeat, electric field is to find out at a particular point, but we are using the Gauss's law, and for Gauss's law we need a closed surface. What we will do, we draw a closed Gaussian surface in terms of a cylinder, and the area of this portion, say, is A, and its vector is outward drawn normal, is in this direction. And both the areas are same. This is also area A, and its vector is also going outward drawn normal. And then this is a cylinder, then this surface, this cylindrical surface. Again here we have three regions. This is region 1, this is region 2, and this surface is region 3. We will calculate the total flux, this region containing and this region containing and this cylindrical surface containing, then we will add up. But to find out the flux, phi is equal to E dot A, we need to calculate first angle between E and A. Let the flux phi is given by the dot product of electric field En, area vector, and Ea cos theta, because I bring the dot product in terms of, will provide us an angle cos theta. Now to find out region by region the electric flux. If I take, suppose this is a cylinder, this is inside a sheet, say suppose this is a sheet, this is like a cylinder inside a sheet. This is a positive charge sheet, this is positive charge sheet. Its electric field will be along this direction, and this positive charged sheet is electric field will be along this direction. So the electric field will be along this direction E, and here it will be along this direction E. So electric field will be this direction and area vector will be along this direction. Here electric field will be in this direction. Also the area vector of this very portion will be along the same direction. So electric field and area vector is parallel at this region and at this region. Here the electric field is in this direction, but this cylindrical part, it is area vector is in this direction. Electric field is along this direction and the area vector is along this direction. The angle is 90. Similarly, at this very point, the electric field is in this direction because this is charged positive sheet, is electric field in this direction, and the area vector is in this direction. The angle is 90. At every point on this cylindrical surface, the electric field will be perpendicular to the area vector. Same at this cylindrical surface, the electric field will be perpendicular to the area vector. But at these two surfaces, these two cross-section surfaces, the electric field will be parallel to the area vector. So, electric field phi will be equal to phi 1 plus phi 2 plus phi 3. So you have phi 1 is equal to, this is region first, that is E A. Its electric field will be same direction, that's E A cos 0 plus phi 2. Here electric field is in that direction, area vector is same direction, that is E A cos 0 degree, and phi 3 on everywhere on cylinder. The electric field is along this direction and area vector is along this direction. Similarly, electric field will be along this direction and area vector will be along this direction. So angle is 90. So this will be EA cos 90. And cos 90 becomes 0, plus this is 1 becomes EA, plus this is 1 becomes EA. So the phi flux will be 2EA, net flux. The net flux given by this sheet will be phi is equal to 2EA. Using Gauss's law, if I use Gauss's law, we know phi net is equal to Q over epsilon naught. It's a total charge inside this cylindrical sheet. Q over epsilon naught. But let me discuss another point. Here, this is a positive charge uniformly distributed in this cylinder, Gaussian surface. This charge over this cross section A, Q over A, area is A, area will be same here, will be same here because the cylinder of same cross section. Here charge containing will be Q same. So Q by A is the surface charge density. So I can write Q is equal to A into sigma, surface charge density. This is equation first, this is equation second. Comparing first and second, you get this phi net, here is phi net, you get 2EA is equal to Q over epsilon naught, or E is equal to Q over 2A epsilon naught. So E will comes out to be Q is equal to sigma times A, or 2A epsilon naught. Or you can write here Q over A is surface charge density sigma. This cancel, so you get E is equal to sigma over 2 epsilon naught. This is the expression for the electric field due to thin charge infinite long sheet. Now this electric field, we have calculated that the charge is uniformly distributed, so charge per unit area will be constant. So charge per unit area will be constant, and 2 is constant, epsilon is constant, so electric field is independent of the distance from the sheet to the point. So this is the expression for the electric field due to a thin sheet, and we concluded from this very point that electric field in case of thin charge sheet is independent of the distance from the sheet. Likewise, E is equal to lambda divided by 2 pi epsilon r, we conclude that electric field in case of line charge varies as linearly with r. Here we don't have a distance r given as this. So wherever you go and how long you go away from thin sheet, the electric field remains in case of thin sheet constant. So first question is derive the expression for the electric field. This expression is called sigma divided by epsilon naught. Second is the conceptual question that in case of thin sheet, the electric field is independent of the distance from the thin sheet. That means electric field remains constant in case of thin sheet. This was the second important question of application part of this Gauss's law. We will go for the next session. Thank you very much.